Hi, my name is Omar Gonzalez, and I have selected a multi-party computation as my topic. I found this topic interesting because it doesn't use cryptographic keys uh, or, in, or encryption. Okay, there is some preliminary concept that I need to go over. These preliminary concepts underline on the multi-party computation. There are two: the threshold secret sharing technique and the Lagrange interpolation. To understand the threshold secret sharing technique, we need to understand an access structure, which is a subset of parties, or P. And P is a finite set of n parties, P1, P2, all the way to Pn. And to some concept for the access structure is if a subset belongs to the access structure and the subset A is a subset of B and subset of P, then B is a subset of the access structure. If the subset A belongs to the access structure, then the subset the cardinality of this subset A must be greater than 0. And the Lagrange interpolation, we'll explain it in the next slides, but it's basically to recover the secret in a polynomial. We will see it. Okay, we have here the threshold secret sharing technique. It refers a method for distributing a secret among a group of participants, of each whom is allocated of a shared secret. So it has two phases. The sharing phase is when a secret is divided into n shares in order to be distributed among n players. And the reconstruction is an authorized subset or authorized structure of players that then cooperate to reveal the secret. T players where T is less than n is the threshold. We can see here the example that we have the threshold as 2, and that means we will need 2 points to recover a secret value. So 4 points are given. So if we use a Lagrange interpolation, we can define the line, and in the line we will find the secret. In this case is 1, the constant term. So in general, it takes t points to define a polynomial of degree t minus 1. Okay, here the Lagrange interpolation polynomial is a polynomial px of degree at the most n minus 1 that passes through the endpoint. So in this case, on the right side, you see the graph that is 3 points, and the polynomial should be of degree 2. On the other side, we have the representation of p of the polynomial p, which is the sum of another polynomial, and this polynomial is computed with by multiplying the x values in this particular order. Pi, the big symbol pi, represents multiplication. Okay, here is written explicitly. The result is a polynomial that defines a line of points provided. So here we can see how the x and y's are computed, and it will output a function or a polynomial. So now here, moving on, what is cryptographic method? I'm sorry, what is multi-party computation? It's a cryptographic method called multi-party computation consists of calculating a public function over secret values from multiple parties without revealing the secret value. Each party locally compute uh, share secrets and share them among the parties. Then using these shared secrets, the parties can compute a function. So, like I said, it is a decentralized method. There is no hard math problems that is underlined on the multi-party computation, and the inputs are the secret shares that parties will generate the secret shard using their own polynomial, and the output is a function that is revealed to all parties. In this function, you will find the desired result or computation. Okay, here is a graphical representation of all the inputs, which are again the secret shares go through a black box, which is the multi-party computation, and then we compute a function which is public or revealed to all players or parties. Okay, here we have different application the multi-party computation can apply. The first one is a sealed bid auction. Is a type of process in which all bidders simultaneously submit sealed bids to the auctioneer, so no bidder knows how much the other auction participants have bid. Then we also have the comparison check that to determine the values are equal or not, greater or less, without revealing the real value. And also we have on the privacy preserving data mining to compute data, or in this case secret shares, and respect the Privacy Act. We also have a secure electronic voting, is to determine the total amount of votes without revealing what the voters have chosen. And a secure addition is to obtain the total sum of values, of secret values, without revealing these values. We will have an example of it. Okay, how does it work? Here is the example. I wanna describe it on a comprehensive example with 5 parties. That's why n is 5. Now each party, like I said at the beginning, each party locally generates a random polynomial. Let's say f with a degree d, and the polynomial holds the secret value. So let's say party 1 generates a fx, and the polynomial has the number 3, which is secret. Party 2 has generated its own polynomial g, and the secret value is also on the constant term 2. So they both want to know, they both want to sum their values 3 and 2, but they don't want to say their values. So then each party calculates a secret share for the other parties using their public ID number within a finite field. We're gonna say the finite field is 41, and the party's ID number are the X values. So if we apply party, let's say party 1 on the f function, well, we get 5. If we take the party 2 ID number, which is 2, on the f function, we will get 9, and so on. So you can see in the example, the party 1 will generate 5 shares using the other party's ID number as X values. You see, so we will have a total of 5. Here, P2 will also calculate its shares with its own polynomial, and we generate 5 shares as well. So you see here G and 1, 2, 3, 4, 5, which represent the party's ID number, and it will output values, which are the secret shares. Now each party sends a generated share to other correspondingly. That way, one will keep one of his share and will send the other 4 shares to the corresponding parties. As well, the other party will send party 1 its shares. Here is a better here is a graphical representation of how multi-party computation works. Like I mentioned, it's a decentralized system. Each party locally generate shares and send it to the other parties. That's how it works. The nodes represent the parties, and the arrows the shares. Each party compute their own share to get a result Y. In this case, it's the sum of the parties 1's secret plus party 2's secret. So here, each party will take the share from party 1 and party 2 and sum it up. Of course, they have to mod it, have to reduce it to be on inside the final field, and it will get 5 Ys. Each party will have a Y, and here is a representation how the result of each party is considered a point. You know, like the numbers, the X values represent represent the party's ID number, and the Y values is the sum. Now we have 5 points, and we need to calculate the sum. With this, we're going to use the Lagrange interpolation to define this line. And if we assume that the threshold is 3, then we will need 3 points. And here, as you can see, using the Lagrange interpolation, well, we get 5 plus 2x plus 2x squared. And this is the output function, and is revealed to all parties. And this makes sense because 3 plus 2 is 5. So we were able to compute the sum without revealing the secret values of party 1 and party 2. So it's in a summary, multi-party computation use a protocol to emulate the trusted party. The parties locally generate a random polynomial that can be used to generate the secret shares. Then the secret shares are distributed among the other parties, and they jointly compute a public function. And the goal here is to preserve the secret values unrevealed. Thank you very much.